Good evening, everybody. Let's get started with today's lecture. We're going to continue with the power series, which we now know is just like a glorified Taylor series as a solution to the differential equation. We're adding together a bunch of polynomials together with the right amount of weights of each polynomial to build up our solution to the differential equation. Now let's do a recap of what we learned so far. We have this generic differential equation, second order, with coefficients p of x and q of x. Now, so far, one of the most important questions we've thought about is, are there singularities to the coefficients p and q? Now, if the answer is no, then you can just write down a standard power series and expand your solution about the point x equal to a, and you're guaranteed that your solution is going to converge everywhere because you have no singularities in p and q, and therefore your radius of convergence is infinitely large. So just try this, plug it into your differential equation, you get a recursion relation that obtains c sub n, and you're completely good to go. Now, if you have singularities in your p and q, but your singularity does not happen at the expansion point x equal to a, then you're still okay. You can still write down the solution, expand your solution about x equal to a. The only thing you need to worry about is that your solution will only converge within a circle of radius going to the nearest point of your singularity in p or q. For example, if you have a singularity in your coefficient p or q happening at x equal to 3, and you're expanding your solution at x equal to a equal to 0. So you're expanding about the origin. You can still write down the solution, plug it into your ODE, and then work your problem all the way until the very end. But you just need to remember that your solution is only valid in a disk about the origin to the point x equal to 3. And therefore, it's going to have a radius of convergence of 3, and your solution will converge everywhere inside that disk. Everywhere outside, you're no longer guaranteed, and it may diverge. Now, that's what we've learned so far. But in many times in science and engineering, you want to develop a Taylor series-like approach to solving differential equations at an expansion point that actually diverges. So there are situations where p and q, both of these guys, or one of these guys, have a singularity, and you want to do an expansion of your solution at the point of singularity. So at x equal to a, at that point, it diverges. So what do you do then? Well, there's a technique called the Frobenius series, which is what we're going to cover today. And the main idea is you can remove or get around that point of singularity at the expansion point where it diverges by putting a prefactor out here that I've shown in green. So x to the r is a new term that you've added in addition to the usual rest of the power series terms over here on the bottom right. So it turns out that the addition of the x to the r term allows you to overcome that singularity. And now the goal is not only to figure out the c sub n coefficients of each of your weights of your polynomials, but also to figure out what the constant r is equal to. So today is all about the Frobenius series. Let's get started. Let's get started with the Frobenius method. A large class of ODEs that come up in science and engineering takes the following form. X squared in front of the second derivative of y, a factor of x times a coefficient p of x in front of the first derivative, and the normal coefficient q of x in front of the function y. All of this is set to equal to 0. Now I'm going to do one operation by dividing the whole equation through by x squared. So I divided through by x squared so that the prefactor in front of the second derivative is just equal to 1. The first derivative now has a p of x divided by x. And lastly, the function value y has a prefactor q of x divided by x squared. Now what's given to you is that your coefficient p of x and q of x are analytic at x equal to 0. In other words, at the value x equal to 0, this function p and q does not diverge. It converges to some finite value. So it doesn't go off to infinity or negative infinity at x equal to 0. But you can clearly see that the prefactor taken as a whole is still diverging on you. So p of x divided by x is diverging on you at x equal to 0 because you have a constant divided by 0, which is infinity. This one, same thing. Q of 0 is analytic, so it doesn't diverge, but Q of 0 is constant divided by 0 squared is also diverging on you out to infinity. So clearly, a normal power series approach cannot be done at x equal to 0 because each of these prefactors, here and here, in front of the first derivative and the function value, are both diverging at the expansion point x equal to 0. Now what we can do is write down what's called a Frobenius series solution, which does an expansion point at the point of singularity at x equal to 0. This is what it looks like. So this is called a Frobenius series solution. So it looks like the usual power series solution where you have the sum of n going from 0 to infinity, c sub n x to the n power. So it's still a bunch of polynomials added together. But because we're expanding at x equal to 0 and there's a singularity at that point for your prefactor, we need to add this extra term x to the r. Now we have one additional unknown. In addition to c sub n, which we don't know, which we're going to find through the recursion relationship, we also need to figure out what r is equal to. We need to find the right value of r that allows us to obtain an expansion at the singularity of x equal to 0. Let's write that down. I've broken it down into a sequence of steps that we'll carry out. So the general procedure is similar to what we've already been doing with the power series. You take your assumed form of your solution, you substitute this solution back into the ODE shown here. So to do that, you gotta take a couple of derivatives, unfortunately. So you take y prime and y double prime of this thing. So you gotta take a bunch of product rules here. A little cumbersome. But you do that, plug it into this second order ODE, and then you index the sum. You take the lower bound, and you re-index those summations. You find the recursion relationships, and this step requires a ton of algebra. So I'm not going to go through it right now because that misses the core point that I want to talk to you about today. The end of that procedure gives you a relationship for r and c sub n, the usual recursion relationship. In addition to the usual recursion relationship for c sub n, you find another equation that will tell you the value of r, which is this exponent right here, the prefactor that allows us to remove that point of singularity at x equal to 0, the origin. And now the equation for r looks like this. Just like that. 0 is equal to r times r minus 1 plus p, this p right here, the coefficient in front of your y prime, excluding the 1 over x. So p evaluated at x equal to 0 times a factor of r plus this last term q, this other coefficient, evaluated at x equal to 0. So both q and p are just going to be numbers because they're functions evaluated at a specific point, so those be numbers. And this whole thing will just be a quadratic equation for r. And this is called the indicio equation. This indicio equation is similar to the characteristic equation when we were solving ODEs with constant coefficients that were second order. You get two roots because you have a quadratic equation for r. And depending on the nature of those two roots, the solution to this quadratic equation, you get different solutions that you should guess to maintain the approach and keep going with the procedure. And depending on the nature of the roots, you should have different solutions of your Frobenius series that actually allows you to remove the singularity at x equal to 0 and are valid solutions to the second order ODE. So let's consider, in this case, 3 different cases in which you'll have different roots that come up. So let's consider those 3 different cases. I've moved the indicio equation that was written down here up here for our convenience because now we're going to find the solution to this quadratic equation for different values of r. You get 2 roots, r1 and r2, And based on the nature of those roots, you'll get different solutions to come out. So case 1 is when your roots, R1 and R2, are not the same. So you have distinct roots, similar to when we were doing constant coefficient second order ODEs, where you had lambda 1, lambda 2 that were distinct roots to the quadratic equation. So distinct roots, and the roots are not offset by an integer. So the difference between R1 minus R2 is not equal to an integer. -3, -2, -1, 0, 1, 2, 3, 4, those are all integers. So the offset is not exactly equal to an integer. Then in that case, the solution is very straightforward. You just take the Frobenius form that I had written down earlier, and you just plug in x is equal to R1, which is one of your roots to this quadratic equation. And everything over here is just the same as your normal power series. And your other independent solution is just x to the other root, R2, which is the other solution to this quadratic equation. And then everything else over here with a different weighting b sub n. And then the polynomial is x to the n. So you have these two parts right here that are both the normal power series with a different thing out in front of x raised to R1 and R2. Easy. And you take these two solutions, y1 and y2, and those will form the independent solutions to the equation right here. So you would just take these guys, plug it into this equation, go down, find your recursion relationship for an and bn, and you're done. Because at this stage, you already know what R1 and R2 are, so you already know your R's, that's done. You just need to find your an and bn, which you obtain from just plugging into the solution. You do a bunch of algebra, you find your recursion relationship, just like how we did last lecture for the normal power series. So that's case 1. A separate case is when you have a double root. So R1, R2 are both equal to R. So this equation is a quadratic, so it can produce double roots, right? Like we saw earlier with constant coefficient second order ODEs. So if you have a double root, then you still have two linearly independent solutions. First one is just simple, x to the r, and then the rest of the summation, the normal power series. But your second solution is a little bit interesting. What you're going to do is take y1, which you just defined up here. So this is your normal kind of Frobenius power series solution with x to the r. But you're going to multiply that function with a log x, okay? Plus everything here, which forms your other part. So x to the r, summation bn x to the n. And y1 and y2 form your two linearly independent solutions to this differential equation. You'd plug it into here, you take a couple of derivatives, blah, blah, blah. You obtain your coefficient weights a sub n and b sub n, and those are your solutions. Lastly, case 3 is a situation where R1 and R2 are equal to an integer. So you obtain your two roots, they're distinct from each other, they're offset by an integer. In that case, the solution looks similar to case 2, except there's one subtle difference. There's a factor of c out in front. So you have y1, the usual solution from up here. We have x to the r1. That's the same solution as up here. So basically, one of your solutions will just be a Frobenius form where you have polynomial x raised to the root value, and then your power series polynomial solution. So that's true for y1, case 1, case 2, and case 3. Now, the second solution tends to differ a little bit based on what your roots are. So in case 3, what you're going to do is you're going to take that solution from earlier, y1, multiply it with a log, and add another unknown prefactor c, and then plus the rest of the part, which is similar to everything else. So now, in this particular case, you do the same thing. You take these two solutions, take a couple of derivatives, plug it into this equation, find your recursion relationships. But in this particular case, you'll also find the value of c. So the value of c will also just come out through the process of finding the recursion relationship. So these are your 3 different cases that you would guess to obtain a solution to this differential equation when your expansion point x equals 0 diverges in this way. Now, at this stage, you might be a little bit overwhelmed by all these different crazy solutions. Power series already was pretty crazy for me. And now you're multiplying it with another prefactor x to the r. There are logs in there. And oh, it's just a little bit overwhelming. Well, let me give you a little bit of motivation for why these solutions come up and why they're important for science and engineering. Because these types of solutions do indeed come up in very common problems. So let me give you a little bit of motivation for why we have to do all of these things right here. The reason why this equation is so important in science and engineering is that there's a large class of problems that frequently come up in cylindrical or spherical geometries. Everywhere. For example, heat and mass transfer. In a couple of weeks, once we start doing partial differential equations, we're going to learn the heat equation. And in particular, we're going to try doing the heat equation in a cylindrical shaped object. Let's say we have a cylindrical rod through which we want to measure the heat transfer of. Let's suppose that there's a water jacket surrounding this heat transfer object. And there's a water jacket around this element because maybe there's an exothermic chemical reaction happening inside this reactor, which is cylindrically shaped, big column, and it's removing heat around the lateral surfaces of the reactor to make sure the reactor walls don't start melting or it doesn't explode. And on top of that, you're given boundary conditions at the bottom and top surfaces of the cylinder. Let's say the top surface is fixed at some temperature 100 C, and the bottom is fixed at a different temperature 0 C, and there's some kind of chemical reaction happening inside this material. Now, to solve this problem, we would normally use cylindrical polar coordinate geometry, where we would base our origin at the lower end of the cap of the cylinder that has some radial coordinate r that sweeps across an angle. So everywhere that along a particular cross-section along the z-plane has an angle theta that tells you where you are in angle. And there's a z-coordinate, an axial direction that tells you where you are in height along the cylinder. Now, in a couple of weeks, we're going to derive the equations that govern this heat transfer problem, and it's going to be called the heat equation. It looks something like this. This is called the heat equation. Don't worry if it doesn't make any sense. We're going to derive it a little bit later in the course, but it's an equation that's incredibly important for science and engineering and all across different systems. Now, the goal behind this problem is to figure out the temperature profile inside of a reactor because you want to know where the temperature is inside of this material. So in general, inside a system like this, the temperature will depend on r, where you are radially, the polar angle theta, and where you are axially along this material, and possibly with time. Therefore, this is a multivariable function, temperature, that is governed by a partial differential equation. Now, there's a couple of parameters inside this system. One is the alpha, that's called the thermal diffusivity. And this thermal diffusivity has other parameters in there like the thermal conductivity, the density of the material, the heat capacity of the material. It tells you how conductive the material is to heat. How easy can heat transfer across that material? Now, this term on the right-hand side, this upside down triangle squared, is called the Laplacian operator. And the Laplacian operator changes depending on the geometry of your object and which coordinate system you adopt. Now, for this particular geometry of a cylinder, we would often use cylindrical polar coordinates. Now, when you then work out this problem a little bit later in the class, which we will do, we're going to do a technique called separation of variables. And in separation of variables, we're going to make a guess that the full temperature profile can be written as a product of a bunch of functions that only depend on a single independent variable. And one of those functions, let's call it capital R, is going to have an ODE associated with it. And that ODE, during this procedure called separation of variables, is going to look something like this. And this ODE, all of a sudden, looks a lot like this one up here. X squared, y double prime, plus x times some coefficient p of x, which in this case is 1, plus q of x, which in this case is just x squared. Now, this ODE is very famous, and it's called the Bessel's ODE. And that's what we're going to cover for the rest of today's class, solving the Bessel's ODE. But I just wanted to return to this grand question of where does it come up in science and engineering? It's not just heat and mass transfer. It comes up in fluid mechanics. It comes up in electricity and magnetism, E&M. It comes up in bending of beams in solid mechanics. It comes up in physical chemistry of finding solutions to orbitals of elements and molecules. So as you can see, it's a very important class of problems that we need to understand. All right. Now that we have a little bit of motivation of where in science and engineering we might see an ODE that looks something like this, let's return to writing down the generic form of the Bessel's ODE and figuring out how we might be able to solve it. The generic form of the Bessel's ODE looks like the following. X squared prefactor in front of the second derivative, a factor of x, and we have this x squared minus a lambda squared prefactor in front of the function you want, y. Now, lambda is a parameter. It's usually known to you beforehand. So lambda is a value that you know. Y is a function of x only, so you'd like to solve this ODE. Obviously, it's got non-constant coefficients, and if you wanted to solve this at the expansion point x equal to 0, you're going to fail if you do a normal power series, because at x equal to 0, it's going to diverge, right? The coefficient here is going to diverge at 0 because you're going to divide through by x squared. This will have a 1 over x. This one will have an x squared minus lambda squared divided by x squared. Both of them are going to diverge at the value of x equal to 0. Now, let's first map this equation back to the generic form up here so that we know exactly what P and Q are with respect to the definition of the Bessel's ODE. So, for the Bessel's ODE, we have the coefficient P of x, which is just equal to 1, because if you go up here, if you map this equation right here with the Bessel's ODE, the prefactor in front of y prime is x times P of x. In this particular case, we just have the function 1. So P of x is equal to 1. Q of x right here in front of the y is simply equal to x squared minus lambda squared right here. Just pull it straight down. Now we can evaluate P and Q at x equal to 0. So when we evaluate the P and Q coefficients at x equal to 0, P of 0 just becomes 1 because the function 1 doesn't vary with x. And secondly, Q of 0 just becomes this parameter negative lambda squared. Now, as advertised, P and Q is analytic at x equal to 0. Clearly, P of 0, 1, Q of 0 minus lambda squared are analytic. In other words, neither of these are infinity. So both of these P and Q aren't diverging to plus or minus infinity at the value of x equal to 0. Therefore, we can continue with the Frobenius series, and we can write down our indicio equation. Our indicio equation looks like this. All we've done is to plug in P of 0, which is 1, into right here. So this R has a prefactor of the value 1. And next, Q of 0 is just simply equal to negative lambda squared. Now, this is just a quadratic equation for R. That looks just like this because the factor of R just canceled, and we get R squared minus lambda squared equals 0. So we get distinct roots equal to lambda. So we get the roots R is equal to plus or minus lambda. Now, just now I said we get distinct roots equal to lambda. Not really true. For example, lambda could be equal to 0. In that case, it would be a double root. So technically, you still don't know whether we have case 1, 2, or 3. You don't know whether lambda is an integer, because if it is, then R1 and R2 will be offset by an integer. You don't know that they're distinct. So in general, at this stage, we still don't know yet. So the general sequence of steps is you plug in to this root, x to the r, with the usual power series form, infinite summation of c sub n, x to the n. You plug this solution, a guess, into this Bessel's ODE. You go through the reindexing, find the recursion relationship. A lot of algebra goes here, which I'm going to skip because that's not the point of what I wanted to focus on today. And out comes a infinite series solution, similar to the infinite series solution we obtained during last lecture for the exponential, e to the negative 2x, was just a summation of a bunch of polynomials. It'll be the same thing here. You'll get a series solution from the guess based on this solution right here. And that series solution will look like this, and it will be the solution to this Bessel's ODE. Now, like I just mentioned a minute ago, depending on the precise value of lambda, you're going to get different solutions to come about because of those three different cases. After you go through this cumbersome procedure, you're going to get a series solution, an infinite series solution, and it's going to depend based on the value of lambda 1 and lambda 2, which are your roots for the indicial equation. In one case, we have a situation where lambda 1 is not equal to lambda 2. And if you think about it, the only situation where that would be true is if lambda were not equal to 0. So if lambda were equal to 0, you get a double root, and this condition would not be true. So in other words, the criterion for lambda 1 not equal to lambda 2 is that lambda is simply not equal to 0. And so this is true, and the difference between the two roots is not equal to an integer. Negative 2, negative 1, 0, 1, 2, 3, 4. Integer offsets between lambda 1 and lambda 2. So hypothetically, if lambda were equal to 3, the roots R1 and R2 would be plus or minus 3. Plus or minus 3 obviously is offset by an integer, 6, which is an integer. Therefore, it would not fall under this solution case. A situation where it would fall under that is, for example, if lambda were to equal a fractional value. Let's suppose lambda were equal to 1/3. In this situation, indeed, the roots to the indicial equation is plus or minus 1/3, the same scalar quantity, plus or minus the negative sign. But the difference between them is not equal to an integer. Therefore, it would fall under this case. Now, fractional values of your roots does come up from time to time, so this is an important case to consider. Now, that's the requirement. The actual solution, which we haven't talked about yet, is written here in pink. So the two linearly independent solutions would be j sub lambda, whatever that is. I'll explain in a minute. And your other linearly independent solution is j sub negative lambda. Those would form your two linearly independent solutions, and we would tack on a constant of integration, a and b, and so your y of x would be your full two linearly independent solutions to this second order ODE. Just like how you might put sine x and cosine x with a and b out in front. So a sine x plus b cosine x. Those would be your two linearly independent solution for Cartesian coordinate ODE that we've already covered so far. All right, so I'll explain what j sub lambda is in just a little bit, but I wanted to move on to another case. So there's actually two cases, as I've written over here, depending on the nature of lambda 1 and lambda 2. So just a while ago, I presented the PowerPoint slide with the three different cases. Case 1 is essentially what this would cover. Case 2 and case 3 are actually the same in our particular situation, as you will see shortly. Let me write down case 2 and case 3 just merged into one overall category of a second solution set. So this is the second grouping of solutions. That's the case where your roots of your indicial equation are equal to each other. So you have a double root. And like I said earlier, the double root happens when lambda is equal to 0. You get plus or minus 0, a double root. Or you have not a double root, but your lambdas, your roots, are offset by an integer. So that would be the case I considered earlier if plus or minus lambda were equal to 3. Therefore, r will be plus or minus 3, and the offset would indeed be an integer. So you can see that this and this condition was just your case 2 and case 3 from the PowerPoint slide. I've just pushed them together because for this particular equation, the Bessel's ODE, you can just write it down like this. So either or, your solution would look like the following, written in pink. So you have their overall solution, y of x, is equal to the same weird function I showed you earlier, j sub lambda, which I'll cover in a little bit, plus now there's another one, a different letter, capital Y of lambda, which is a function of x. So at this stage, you're probably wondering, what the heck are these functions? Let's cover these right now. This one, these functions. What are these functions? Let's talk about that now. All right, let's first talk about j sub lambda, which is this long and ugly expression shown on the right-hand side. Sum of n going from 0 to infinity, -1 to the n power, divided by n factorial times this thing right here called the gamma function. And the argument of that is n plus lambda plus 1, all multiplied by a function of x. So this is where the x functionality comes into place. X divided by 2 to the power 2n plus lambda. So there's a lot of things going on. First of all, in the prefactor, there is a gamma. What is this thing? Let's go over to the screen where I wanted to show you what the gamma function looks like. So the gamma function is just a function taken from the input. So what I'm plotting here is the gamma function evaluated at some value z. So if I were to plot it, it looks something like this. So what I'm plotting here is this function gamma with the argument z as a function of z along the x-axis. So what you can see is that for z bigger than 0, so when the argument is bigger than 0, it just is a function. It's a nonlinear function that is defined for all positive values. Okay, so for everything here, it's well-defined, continuous, over here for positive values. But for negative integer values, you get discontinuities. So right at 0, right here, this dashed red line has a discontinuity. It jets off to positive infinity, negative infinity. Between 0 and -1, it has a well-defined function. And then at -1, it jets out to infinity, -2, -3, -4, etc. So all non-negative integers are fine. But when you have negative integer values, this function diverges on itself. But if you go back up to the board, you can see that this argument, n plus lambda plus 1, is going to be whatever it is. If lambda were to be 0, which is this case down here, if lambda were to be 0, then n plus 1 will always be integer values, and it'll always be positive integer values. Therefore, this thing right here is just a number. So I don't want you to be afraid of, oh my gosh, there's this mysterious Greek letter that I don't understand. It's some function, a mysterious function I don't understand. Don't think of it that way. Think of it as it's just some number that takes in an argument that changes with the given summation index, and you just slot that number as a prefactor. That's all that is. Okay? If lambda were to be a fractional value, then you would get a non-integer value here, but no big deal. You just use the gamma function to have a defined function right here. Okay? So just think of gamma function. It's just a number, a prefactor that comes out in front. Okay, so what else is inside this prefactor? -1 to the n. That's also a pretty common thing you've already seen before, because you've seen, for example, exponentials or cosines and sines that also alternate in sign, right? It's just the Taylor series would alternate in sign for sines and cosines. So you have seen this before. This n to the factorial, also you've seen before for exponential, sines, and cosines. My English teacher in high school used to think that this factorial was like an exclamation mark. N! It's n! It's got to be n! So Everything here is just a prefactor that you're all familiar with. The x functionality comes over here, x over 2 to the 2n plus lambda. So when you actually think about it, it's just another polynomial power series, just as you would expect, because you're going through this whole procedure. You're taking this polynomial summation, plugging in there, so of course you get a polynomial solution as your output. Okay, so it's really not a big deal. This is kind of analogous to sines and cosines for what you've seen for the ODE, where you don't have this middle term, essentially, right? A linear constant coefficient second order ODE could admit solutions that look like sines and cosines or exponentials, and that also has a series summation that looks something like this. You have a negative 1 to the n power, you have this exclamation n factorial, and you got a bunch of polynomials multiplied against it. So it's really no different from functions that you might have already seen before. You're just familiar with sin, sine, and cos, cosine, and that little e to the power. You're just familiar with those functions. J of lambda is just that name. It was just a name given to a power series. And this J sub lambda happens to have a name, and that name is called the Bessel's function of the first kind of lambda. Let me just write that down. So this is called the Bessel's function of the first kind, order lambda. All right, so I'm going to plot this function for you in a little bit, but let me just go through the other function y sub lambda and tell you what that looks like. So the y sub lambda looks something like this. You take combinations of j sub lambda, which we just defined, that's the Bessel's function of the first kind, and you actually tack on a cosine of pi times x minus j sub negative lambda. So you just literally go to here, plug in negative lambda into this expression, all divided by sine of pi times x. And this function is called the Bessel's function of the second kind, order lambda. Okay, so again, all you need to think about in terms of y sub lambda is it's just another series solution. You're going to take some j, plug it into here and here. It's going to have some cosines tacked into it, but cosines and sines are just another power series. It's just a bunch of polynomials added together. So the product and the division and the sum of all of these things will still just be a bunch of polynomials with crazy weights that look like this added together. So for a known value of lambda, which you will already know because that's a part of your problem, lambda is a known parameter. It's going to be known to you for most problems in science and engineering. So you know what lambda is. So given a lambda, you're going to cycle through different summations of n, and that's going to give you a well-defined prefactor, which will just be a number. And you're going to take that and cosine, which again is just going to be a bunch of summations, and you have it. So for a given value of x, you're going to get a number that pops out for each value of x. All right, so this just looks like mathematical gibberish. So let's just plot that and see what it looks like. So if we go over to the MATLAB screen, what I've done over here is to plot the Bessel's functions. So I'm going to first plot the Bessel's function j sub lambda. And in most problems that we'll be covering, it turns out that this lambda parameter is going to be equal to 0. Therefore, what I'm plotting here is j sub 0. So lambda is equal to 0. J sub 0 as a function of x, here plotted along the y-axis as a function of x, the argument of the Bessel's function of the first kind of order 0. So we can see is that the origin, it peaks to a finite value, and then it goes down, and then it goes back up, down, back up, down, back up, and it just oscillates, but the amplitude goes down as you go away from the origin, and it's symmetric about x equal to 0. Therefore, if you go to negative x or positive x, it's symmetric about the origin. So graphically, in 3 dimensions, this is what it would look like. So I'm plotting here along the z-axis here. That is the magnitude of the Bessel's J0 function as a function of x and y, which are kind of like in two-dimensional space. So what I like to think about is it often appears in cylindrical polar coordinates. So if you were to drop a small little rock or a pebble in a quiescent lake with no ripples, when you drop that stone or pebble into that lake, it's going to create ripples that emanate from the point at which you drop it. And the ripple is going to look something like this, that dampens as you move further and further away. So I like to kind of think of this image of the Bessel's function kind of being like a calm Zen pond. I close my eyes and I think of like a very calm pond or lake, drop a pebble, and just look at the ripples fall away. So, as you can see in this figure, the Bessel's function looks a lot like sines and cosines. It crosses the x-axis many times. It just dampens in magnitude as you go further away in distance, but still it will just continue over and over again as you go to x equal to infinity. Now that's J0. So that's the Bessel's function of the first kind of order 0. Now if I were to plot the Bessel's function of the second kind, again of order 0, it looks something like this. So let me just plot up both of these guys together so you can see them both. So here on the left, we have the function I just showed you. On the right, we have the Bessel's function of the second kind of order 0, again plotted as a function of the argument x. So the overall features of the graph are similar. It has ripples that go away as a function of distance. But the one key difference between the Bessel's function of the first kind and the second kind is that the second kind, y0, diverges to negative infinity at the origin. So you can't really tell because I've truncated this graph after negative 2.5 or so. But this point right there goes all the way down to negative infinity. So the Bessel's function of the second kind, y, is not defined at the origin. It jets off to negative infinity. And actually, that's a very important point. In many problems that we'll solve in cylindrical polar coordinates, we're going to have a boundary condition at the origin. So imagine you have a cylinder, and there's radial polar coordinates pointing out from the center of the circle. And you're going to have a boundary condition at the edge of the cylinder at r equal to r naught, for example. But at the origin, you're going to need another boundary condition, a constraint. For example, the temperature can't diverge off to infinity, or the concentration of reactants can't diverge to infinity. You can't get mass flux into the origin. And that problem is going to have two linearly independent solutions, which are going to be equal to J0 and Y0 up here on the board. Therefore, you're going to have two solutions, and you're going to use the boundary conditions to figure out your coefficients or constants of integration A and B. Now, when you plug in your boundary condition at r equal to 0 at the origin, or x equal to 0, this y sub 0 solution will diverge to negative infinity. And physically, you can't have concentrations or temperatures diverging to negative infinity. Therefore, the only way to make that boundary condition or constraint true at the origin is to set your constant of integration b going to 0. If that's the case, the second term dies, and all you're left with is just the Bessel's function of the first kind, and that's your solution. And that's how you would use your boundary conditions in a real science and engineering problem to figure out your constants of integration. So, what I wanted to talk to you about with regard to Bessel's function is that it's nothing different like with sines and cosines. So I don't want you to be afraid of these types of functions. So these functions, while they look scary and a little bit intimidating, it's just like sines and cosines. If you didn't know about sines and cosines, if you didn't learn about them in geometry back in middle school or early high school, and if I just said, oh, there's this thing called sin, you'd be like, what are you talking about? What is this sin? It's really spooky to me. It represents this infinite summation of a bunch of polynomials. That's really spooky. Well, it's the same thing for j lambda and y lambda. It's just a name given to a bunch of polynomials added together. Okay, That's all I wanted to cover with regarding the method of Frobenius. And in particular, I want you to remember the Bessel's ODE because that's going to come up again in our class once we start solving partial differential equations, and also in general in science and engineering. Whenever you have cylindrical coordinate geometries, you're often going to see the Bessel's ODE. When you have a spherical geometry, like a spherical catalyst pellet that conducts a chemical reaction, in that spherical particle, you're going to have the spherical Bessel's ODE. Again, they're all similar, like sines and cosines. We'll get more to that in the second half of the class, but until then, I hope you have a wonderful rest of the day, and I will see you next time. See you then.